So the symbol we use for the book used for inner product is this triangle bracket, and V1, V2. That's the sorry, that's comma, and this is equal to the transpose of V1 multiply V2, which is basically the elementalized product, element I times element J dot. This actually is really my handwriting doesn't really make. So let's just use the calculation to show this. So in this case, we have let's say in the book example, we have the 5, 3 minus 7 with the another vector 6, 2, and 0. So, and then we basically change this to 5 times 6 plus 3 times 2 plus minus 7 plus 0. $36. There. So basically element-wise, the element-wise product. So my apology for my handwriting. Okay, so that's the inner product. Now this is a real number. For complex number, the book also gives some other rules like scalar, commutative, associative rules. This is actually the book for the complex number. This is the rule we need to remember. We probably have to use it for some implementation. For the complex number A and B, so instead of the transpose, we now need to do the conjugated transpose. So conjugated transpose A and B, and the inner product, the product will basically is also the trace of so I actually have a Python code written. That's so in the book there's the equation. Yes, that's the book equation 2.1110. So I actually have written a Python code to demonstrate that. And that's the, yes. So let's see. Trying to see whether this is from the book or not. 1 plus I. Is that from the book? That seems to be an example I made up myself. Yeah, that's the example I made up myself. Okay, so let's see. We now have two matrix. Okay, that's 1 plus I, 2 minus 3 I, 3 plus 4, 4 minus 1, and then another matrix B. So we want to calculate the inner product of A and B. Inner product A and B. Okay, that's the inner product A and B. And then we calculate the A transpose, A conjugate transpose, A conjugate transpose, and then times B. So that's the A conjugate transpose of that B, that's the matrix. And then we calculate the trace of that. And then we want to see whether they are the same or not. So the trace of A conjugate B is 133 minus 12I. That's correct. Yeah. So basically, this is just a calculation to verify that formula. So that's the yeah. The book also gave the trace definition there. So that actually that's in the equation just before it. Yeah. It turns out in quantum computing, the Hilbert space is the inner product, or in fact, the so-called complete we can just take the word as it is. Yeah. So it's a complete space of complex inner product. Yeah. So uh, for the time being, let's just take the concept that it is. So, and the next part of the book, this may be easier for, especially for many of you already using this in signal processing, eigenvalue and eigenvectors. Oh, on the top part, there's also another definition distance. Sorry, I forgot to mention that part. Move it a bit. There's actually another definition here called distance. Distance is really a bit easier to understand. Let me see where the book's definition. Yes. So the definition basically for any vector v1, v2, the distance basically we first do a geometry, do a vector, and then take the modulus. That's basically the distance. So distance is always a real number. In a way, there's no imaginary distance here. So. Okay, so that's the distance. And then the eigenvector and eigenvalue, many of you probably already familiar with this. Is basically the definition of the eigenvalue is basically, oops, no, I used the wrong pen. Well, a matrix times a vector become a scalar times a vector, and that C will be the eigenvalue. This C will be called the eigenvalue. Oops, this C will be called the eigenvalue. That's the eigenvalue. So and let me see and the example, the advantage of that you can see from the matrix multiplication become a scalar times a vector. Oh, someone in the chat window. Oh, someone say the Euclidean distance. I mean, if it's in a real number, yes. For the imaginary number of multi-dimension, it may, I guess you can interpret that as a Euclidean distance. Yeah. So I have to double check whether when that it does look like at least in the real world, real number system is equivalent to Euclidean distance. So let me go to my Python code to show the eigenvalue example. Oh, I showed the wrong thing. Too many windows on my computer. This one, the wrong, correct one? Yes, this is the correct one. So eigenvalue and eigenvector example. Here, this is actually a real matrix. And I decompose that eigenvalue and eigenvectors. So print out the eigenvalue, 3 and 2. This must be from the textbook. Oh, yes, this is from the textbook. So eigenvalue is 3 and 2, and the eigenvector will be 1, 1. That basically is a scalar. The 0.7, 0.7, 0.4, that's the 1 and 2. And those are apparently normalized. Yeah. This one is basically 1, 1. This one basically 1 and 2. So, so does it make, this must be 1, 1. This one is 1 and 2. Yes. Eigenvalue 3 goes, 3 actually goes to 1, 1. Huh, the way this plotting, okay, my apology, the plotting seem to doesn't go with the arrow. Okay, this is a bit disappointing. Okay. Yeah, the legend isn't overlaid with the actual vector, but the print information is correct. Yeah, eigenvalue 3 and 2, eigenvector, this is basically 1, 1, this is 1, 2. So and below is just a different version trying to plot it in a different way. 3, 1, 2. Yeah, on the top I printed all together, at the bottom, I try to print it the one by one to verify the eigenvalue and eigenvectors. So for eigenvalue is 3, the vector is 1 and 1, basically is the 0.757. For eigenvalue 2 is 1 and 2. Something is wrong here. Eigenvalue that should be 3. Oh, I see. Yeah, this is not good plot. It should label eigenvalue, actual eigenvalue instead of label. Eigenvalue 1 is 3, eigenvalue 2 is 2. So yeah, this is not good illustration. A bit confusing. Yeah, eigenvalue, this 1 is 3, 2 is 2. So yeah, so I think these two plots should be exactly the same, but somehow they are not. Oh, I multiply by the eigenvalue there. Okay, I see. When I plotted you can see the vector is that multiplied by the eigenvalue. So this one is 0.7 times 3, that would be 2.1. That's why it went out of it. Sorry, I didn't realize that this line, the eigenvector actually is multiplied by the eigenvalue. So this 1 and 1 become 0.7 become 2.1 now. Okay, that's right. Okay. And the top, the eigenvector is just plot as is. At the bottom, the eigenvector is plot as the multiply of the eigenvalue. But the point is, you see the direction doesn't change. It's just the scale are changing. So it's actually good. It does show that the eigenvalue and the eigenvector, when they are multiplied, it doesn't change the direction. It just increase or decrease the length of the vector. So, uh, okay, yeah, that's like it is indeed makes sense. Okay, so this is the eigenvector eigenvalue, and the next two part will be touch on the two very important concepts in for quantum computing. That would be the Hermitian and unitary matrix tensor product. So that would be, let me go back to my iPad again. Let's first talk about Hermitian matrix. So the definition of the Hermitian matrix is if a matrix, the Hermitian conjugate transpose of a matrix is equal to itself, and this is called a Hermitian matrix. So the other, you can look at the Wikipedia, see there's a lot of different name of this. It's also called the self at the joint. And the book actually used a dagger. And the book used a dagger, but that is really hard to write by hand. So using an edge is much easier. So, for example, the book gives this example: 5, minus 5i, 6 plus 16i, I 13, 7 minus 2.1, 7 6 minus 69. And how about we write a Python code to show this is Hermitian? I actually have that. Do I have that in the example? No, I do not. Okay, very good. So you can actually look at my own code as an example, try to write your own code to see whether the book example is Hermitian or not. So how about we work on it for 2 or 3 minutes and someone can share your screen to see whether you can show that this metric is Hermitian using Python code. So. Okay, can I have someone to willing to share their screen? Let me stop sharing my screen. Oh, sorry, it looked like I logged out of my Zoom from my iPad. That's not what I mean. So, push the wrong button. Okay, any student want to willing to share?
Sure, I'll bite.
Joshua? Yeah, do you?
I didn't write it in Python, but I did get it in MATLAB.
Sure, no problem. MATLAB also works. Yeah, so.
Yeah, so essentially I have a function. It's a Boolean function with a true or false output where I if the sum of A or the sum of elements in A equaling A transpose is equal to the total number of elements in A, then I return Y is true, and if they're not equal, then I return false. So I don't know why this isn't.
Oh, okay.
All right, so I have A here. I'm trying to see why this isn't. So this should be 5, 4 plus J5, 4 plus J5, 6 plus J6, 6 plus J6. So let me do A. Sorry, I'm trying to see why these aren't. Okay, so the complex conjugate isn't the same. So let me try.
I see. So MATLAB is a native programming language.
Yes.
Okay, nice.
There we go.
Okay.
All right. So if I take the conjugate of the transpose, yeah, then I get the transpose without it taking the complex conjugate A, and then the conjugate of.
What is numo A? What does that function does?
That's the total number of elements comprising A. So if A is a 3 by 3, that returns 9. So it's num elements or number of elements.
Okay. So you are not really entirely examining the entire matrix itself.
I am.
Not if function. You are not entirely. Oh, wait. A equal A. It is basically you are summing up the true element in that one. Oh, that's correct. Yeah, that's correct. Okay. Thank you. I'm trying to understand that line of code what it does. Okay, that is correct.
The benefit of MATLAB is it does automatic parallelization. So MATLAB stands for Matrix Laboratory.
That's
so
right.
It does a lot of automatic full matrix things without having to iterate through loops, and that parallelizes it across the ALU and the CPU and the GPU.
I see. Nice. Yeah. Okay. Anyone use a Python version? Justin, Hannity, Lokis.
Yes, I did.
and-
I used your code.
Okay,
And
Hannity, can you show your Python code?
sure.
Yeah. You'll be really impressed someone used Java wrote this.
So as basically this is the one that I use. Can you see my screen?
Oh, can you make it a bit bigger? It looks very small on my screen.
Sure. Just remove that. I don't know, it's like I'm not familiar with this interface from IBM. I'm using the lab for it. But is it better now?
Interesting. You are working in the IBM Quantum Lab directly.
Yeah, I'm trying to get
Nice.
familiar with it. So I use the lab for it from it, and I just copied your code and I
Okay.
entered the matrix here,
Mhm.
and it says the matrix is
Is permission.
yeah.
Okay. Nice. Oh, gee. So the code worked directly in the IBM notebook.
Yeah, I just copied that and pasted here.
Oh,
and it
that's
worked.
nice. Okay, thanks for trying this. Okay. Yeah. Okay. Yeah. Yeah. Well, actually, it's good that you already trying use the IBM.
Yeah, I just wanted to get familiar with it so as not to be struggling later if there is any assignment or something that because I heard you
Nice.
saying you're gonna ask us to do something with it. So,
It is
yeah,
nice. Yeah. Yeah.
standard preparation.
Yeah, there's actually a lot of things we can work in the IBM. Now the trouble is many of the IBM code hasn't been updated. So at least when I try to run the tutorial, many of the code doesn't run anymore. Yeah, that's always an issue when the software release new version every now and then. The old code just doesn't run anymore.
That's right.
Yeah. Okay, thanks for sharing this.
No problem. I'll stop sharing now.
Thank you. So I have the Colab version. So this is the matrix from the book. I printed out. I actually calculate the conjugate transpose and print it out, and so you can compare. That's the conjugate transpose. We can visually verify this. It is the same as when we put in. I guess we can reformat, make it easy to read. Ah, 713, 7. Yeah, this is a 0 jet, so it's just a real number 7, 6. Yeah. So you can verify it should be, it should be exactly the same. Yeah. So okay, so I can also save a copy back on the GitHub, and I say updated with permission example from the book. Which example is that? Permission example from example 261. Okay, so I add a comment say. Yeah, it actually automatically goes back to my GitHub and updated. So if I updated with the permission example 261 in textbook. So yeah, but it is nice to if I don't like this I can go back to the previous version. Yeah, I first started 5 days ago, tried to work on permission metric test. Okay, so and the next important concept is the unitary matrix in the book. The unitary matrix definition is basically a matrix times inverse of itself become the identity matrix. So we can, let's see whether we have an example here. This is the example I have using a square 1 over square root of 2, 1 over minus 1. It looks like I made up this example. So no, this is actually not the unitary example. That's the conjugated transpose versus inverse. I don't have a unitary example. I thought I had one. Okay, it looked like I mislabeled. This is conjugated transpose versus inverse. Checking that. I made a mistake here. This is actually not a unitary example. Okay, let's redo this. This is actually inverse versus the conjugated example. So let's rewrite this one. Sorry, I just realized I made a mistake. Unitary metric example. This is actually compare conjugate transpose versus inverse. Okay. Okay, let's all work on it for a few minutes. Let's see whether we can come up with an example. We can just use the book example. On the book example 262. So let me see. How do I do this? Okay. Anyone had the progress on this unitary matrix example? Either MATLAB or Python, I guess. So,
Dr. Keen, I think that the original example that you had in GitLab did check for a unitary matrix.
you did?
I had copied and pasted it in VS Code, and it does check for.
Oh yeah. It does. Okay. Thank you. Yeah. Okay, I guess then it is my comment are wrong then. Okay. Oh, thank you for correcting me. Yeah. That's right. Yeah. Okay. Yes, it indeed check for unitary. Yeah. Oh, gee. I guess it is my comment are wrong. Yeah. Okay. Thanks for correcting me. Oh, gee. Yeah. It actually indeed check for unitary. Yeah. So. Well, it's still good exercise, I guess. Yeah. So, yeah, it actually it had the material of this, then check. So conjugate transpose and then inverse check for inverse conjugate transpose. It is the same and it is unitary. Oh, this only work if it's a real matrix actually. But it not necessarily the case if it's the imaginary, does it? Okay, I don't remember in linear algebra the actual not all metrics are invertible, but I'm not sure whether all metrics have a conjugated transpose or not. I don't remember this. Dan, you are the one have to have a qualified exam soon. is all complex matrix have a conjugate transpose or not?
It should, they all should have a complex
I think
conjugate
so.
transpose.
It should all have. Okay. Then we have this all matrices have conjugate transpose. If all the matrices has also, but not all matrices are invertible, then we have this seem to be a logical conflict here. All matrices have a conjugated transpose, but not all matrices can be invertible. Oh, I see. Only for unitary matrix, the conjugate transpose and invertible are the same. I see. Okay, yeah. So maybe this does make mathematical sense. Okay, yeah. So okay, for a moment, I thought this is wrong. I guess for unitary matrix, that condition is always satisfied. So okay, I just rewrote almost exactly the same thing. I realized it's already written down here too. Yeah. Yeah, that's a bit different example, but it is the same thing. Yeah. Okay, thanks for gee, I guess yeah. And for let me rewrite the comment. For unitary matrix, conjugate transpose and the inverse are equal. Yes, that's right. Unitary matrices are always invertible. Yeah. Okay, this makes sense now. Oh, okay, are equal. Okay. Okay, thanks. This is supposed to be a simple Python exercise. It does actually clarify some mathematical concept. Okay, thanks everyone. Unitary test, unitary and conjugate transpose test. Okay, all right, good exercise. So. Okay, finally, it's the tensor product, which is take me a while to I'm glad I'm trying to give a lecture on this. It really also helped me understand the tensor product versus the matrix product. So the tensor product is the definition of the tensor product was as a quantum product. We can use this example try to illustrate this. So we have a two vector V1, V2. The tensor product is something called I forgot how to pronounce it.
It's the Kronecker.
Kronecker product.
Yeah, they use it a lot in machine learning.
You use that in machine learning. Okay.
Yeah.
So that's Chronicle. Can you how to pronounce this again?
Kronecker.
Kronecker. Okay, I guess that's the emphasis. Kronecker product. And so vector 1, vector 2, the tensor product. So we have 2 by 2, 2 by 2. Now we have 1, 2, 3, 4 element now. That looks very so the book actually does have an example to explain it. Yeah, so book there's a figure called, let me draw using my iPad because officially I'm not supposed to show the copyrighted material. So, so I'm going to draw using my iPad. So the tensor product if we have a A0, A1, A2, A3 times another vector B0, B1, B2. And what this does is actually expand this into A0 times product B. Okay, those just B. A1 times B. So, and then we have this really long vector of tensor. And then this will be the first one, and then A1 B0, A1 B2, B1, A1 B2, and then with A2, A3. So that's the tensor product. And let's go back to the example to illustrate this. So this is we have two vector V1, V1, V2. V1, V2. The red is the real part, blue is the imaginary part. This is shrink a little bit. Okay. So V1, V2, V1 the real part is 1, V2 real part is 3. One, one, two, two. 1, 1, 2, 2. V2 is 3, 3, 4, 4. 3, 3, 3, 4. Is that correct? Yes, that is correct. Yeah. So I see. So it actually put the imaginary real in the same vertical axis, just labeled by different color. So that's correct. So and then we compute the tensor product of V1, V2, and then visualize the tensor product. And so from a 2 by 2 matrix, we should have a 4 by 4 tensor product. That's the tensor product. And these are just for 2 tensor vectors. If it's a tensor matrix, a matrix tensor product, that will be even more complicated, I guess. 2 by 2, 2 by 2 now become 4 by 4. It's not sure how to visualize that. Not to be really multi-dimensional visualization. I'm not sure how to visualize that one.
It's
but
more,
yes.
kind of the term that we use in machine learning is more of a mapping function. So the tensor product is kind of mapping each element of A through B. So if you, it's kind of where so machine learning is all about classification, where each element of A may be a feature, and B is designed to take each element of A and map it to a certain class. That makes sense.
An interesting way. I guess that's the application of tensor product. But in this case, the tensor product in quantum computing, the important part is from the book, one vector is one quantum state. Another vector is another quantum state, but the tensor product is a way to describe both quantum state in one tensor, tensor vectors. That's the book's explanation why you use tensor product for the quantum computing system. So. Yeah, I guess the book also mentioned the mapping a lot about using this as a way of mapping. So I guess the tensor product used a lot in machine learning and quantum computing quite a lot. So, thanks for bringing that topic up. Yeah. It's still quite interesting how I guess we don't have to visualize this. But this is I found this is quite interesting. The tensor product of the 2 complex vector visualize in this progressive way too. Does it make sense?
Do we know which red line corresponds to which blue line in the last graph?
Good question. I'm trying to understand this. Yeah.
I think if we could color them somehow differently, it might be a little more descriptive or interpretable.
Oh.
Yeah, so on the output tensor, that element at 0, 0 is the element of 0, 0 for the first vector times the element at 0, 0 for the second vector. And then on the tensor element for 0 or 1.0, that's the element of vector 1 at 0 and vector 2 at 1. I believe so.
Can you annotate? I'm going to stop sharing. Can you use your screen to annotate? Can you share your screen, annotate what you are trying to say? Yeah, it looks like only the one who present can annotate it. This is on my GitHub, so I can copy paste that code there. You can present the screen and try to explain what you are trying to say.
Okay. Can you just give me the numbers? So
I
let's
put
define
I put
vector
in
one.
the, oh,
Okay.
I put in the chat, the code. Give you the number, what number, the vector?
Yeah, the vector numbers. Yep, you're using for the multiplication. Let me scroll through.
V1, V2, I put that in the chat.
It's 1 plus j, yeah. And then the second one is 2 plus, sorry, 3 plus 3j. Yeah, we made it.
Yeah, 1 plus 1, 2 minus 2, 3 plus 3, 4 minus 4.
Right.
Sure.
So so we have these. If I transpose V1, so let's say equals V1 transposed times V2, it should give me a square matrix, right? So I get, so in the output at the bottom, you can see I get
2 by 2, is that 2 by 2?
V1 of 1 times V2 of 1 would be 0.6. Oh, I need to take the conjugate. Right, so if I take V1 of 1 times V2 of 1, I get 0.6. Then if I take V1 of 1 and then V2 or 2 of V2, then I get 8. So the first row of this will be the first element of V times all the elements of V2. And then the second row here will be the second element of V2 times all the elements of the second element of V1 times all the elements of V2. So let's so let me try something.
Is that the result that we got from the... Oh, sorry. That's your results seem to be the different from what I got using Python code.
Did you do
The tensor product I got is 0, 6, 8, 12. Oh, that's correct. Sorry, it is the same. Sorry. I got the same result. Yeah, sorry.
Yeah.
0, 6J, 8, 0J. That's correct. I got the same result from Python code. Yeah.
okay?
Yeah.
Excellent. So those are our two vectors. What's the vector? The x limit is 0. Okay, so we've got v1 vector there and the v2 vector.
Can, can you see? Can you plot it? See what's coming out of that?
That's essentially what we're getting there.
Oh, is it running or you are waiting for something? Oh,
Are you
No,
displaying
that's the.
plots and we're not seeing them?
Why not?
oh, is it? Do you have a pop-up window
Oh, whoops.
elsewhere? We are not seeing that.
Yep.
Oh yeah, now
Are
we
you seeing
see.
that now?
I see.
Yeah.
I see. Okay. This is interesting. 1, 2, 3, 4. Oh, you are plotting 4 product separately. That is interesting. Uh, huh. That's interesting. You are also plotting the tensor product separately. Real number. Wait. Is that the real number times that? That
Yeah,
shouldn't
it's
be.
the real and imaginary component.
Wait. Can we actually do that? Really? Hold on. I thought that I guess you could break it down. I see. Okay. Uh, okay, but this is different from what I got in Python code. In my Python code, any real number, I also got 4. Oh, that's right. You also have 4. So you had the result is 1, 2, 3, 4. Okay, this visualization actually confused me more than explain things to me for some reason. Okay, the MATLAB. I'm trying to compare your MATLAB figure with my Python plotted figure.
Mhm.
It's
Yeah, so
not
you're plotting the real and imaginary component together. What I can do,
okay.
um, Do that for V2 also. It actually may make more sense if we plot the polar representation.
Mhm. Uh, oh yes, that's another way to look at it. Yeah, using the polar representation to show that. Yeah.
Actually, what I'm going to do.
Yeah.
And make this one figure. And I'll just start with another figure. Right.
That
Okay.
is that is really different from what I got in the Python code.
Mhm.
Okay, but this is a good question for everyone trying to figure out after the class and to figure out the proper way to visualize tensor product. It's probably only applicable for simple cases. I mean, with multiple dimension, it's really hard, become harder and harder to visualize. But 2 by 2 seems to be still worth trying. So yeah.
Mhm.
Uh,
Yeah, so you get the imaginary component, the rectangular representation on the left, and then the polar representation on the right. And without digging deep into the mathematics, it somewhat does make sense because V2 is rising along with V1. So as you multiply V1's first element by V2's first element, you get the smallest number.
So the blue is the imaginary. What is the blue you present at the bottom?
At the bottom, that's the magnitude of the tensor product. So on the left, I have on the top, on the top right, I have the magnitude of V1 and the magnitude of V2.
Okay.
So V1 is the blue one, and then V2 is the orange one. And then I take the tensor product of V1 and V2, and then I calculate the magnitude of the tensor product. And as V1 and V2 increase, so does the magnitude of the tensor product.
I see. Okay. V2 16. Okay, thanks, Joshua. Uh, Justin, Dan, and Hannity, Lokesh, question to Joshua? Okay, this is a very productive class. Everybody is learning new things. Or actually, at least explore what I thought we thought we understand, but still do not know how to explain it. So, yeah. So, okay, let's conclude for today. We covered actually we covered a lot. Inner product, Hilbert space, eigenvector, eigenvalue, permission matrix, unitary matrix, tensor product. Gee, we really covered a lot. Actually, we also run over time again. Okay. So next, I'll see you next time. Next time we'll go through chapter 3 then. Yeah. Bye, everyone. We're going to meet again next time on Zoom. So, bye, everyone.
Right, thank you.
I
Bye.